Let's leave the Milky Way sound simple when you say it out loud, but the universe has a brutal answer waiting. You're not built for this, and neither is your tech. Before you ever see the galaxy thin out, radiation is drilling through your DNA, your bones are dissolving in microgravity, and your closed ecosystem is quietly drifting toward failure. In this video, we'll crank a starship up toward a fraction of light speed and follow it step by step until we hit the exact thing that kills you long before you ever reach the edge. But before we continue, please subscribe to the channel if you enjoy the video. Let's continue. Right now you're on a planet that orbits a star, and that star is orbiting the center of the Milky Way at about 220 kilometers per second, around 137 miles per second. Not per hour per second. At that speed, the Sun takes roughly 230 million years to complete one lap around the galactic center. You are sitting about 26,000 light years from that center, inside one of the spiral arms, in a rotating disk of hundreds of billions of stars. So when you say, "I want to leave the Milky Way," you're not starting from rest in empty space. You're a passenger inside a huge spinning structure. Here is the key point. You are not going to the next planet when you talk about leaving the galaxy. You are talking about climbing out of a system that is about 100,000 light years wide and about 1,000 light years thick in its main bright disk. That disk is like a flattened swarm of stars, gas and dust, and you are buried inside it. To get clear of it in any meaningful way, you have to cross distances that are thousands of light years, minimum. On human scales, even on civilization scales, that is basically off the charts. So then what does outside the Milky Way actually mean in a strict way? Is there a real edge? A sharp border? Where one side is in and the other side is out? No, there isn't. The galaxy doesn't end like a hard wall. The density of stars just gradually drops as you move away from the center and the plane. Astronomers try to make sense of this by dividing it into regions. There is the bright thin disk, where most of the stars and gas and dust live, and where the spiral structure is. Around that there is a much thicker, dimmer, stellar halo, full of old stars and globular clusters spread out over tens of thousands of light years. And wrapping all of that, there is the dark matter halo, a huge invisible cloud of mass that may extend 10 times farther out than the visible light from the galaxy. So your definition of outside really matters. If you say, "I just want to get past the bright disk, I want to be above the plane where I no longer sit in that glowing band," then you probably need to go something like 5,000 to 10,000 light years straight up. That is, perpendicular to the galactic plane. That would put you deep into the stellar halo, where stars are far apart, and the Milky Way looks like a thin, bright strip behind you. But if you say, "I want to be beyond most of the galaxy's mass, I want the Milky Way to be a small object in my sky," then you start talking about 100,000 light years or more from the center. That is a different level of escape. Now you hear light year all the time, but your brain probably does not feel what that really means. 1 light year is the distance light travels in 1 year, moving at about 300,000 kilometers per second, around 186,000 miles per second. That distance is about 9.5 trillion kilometers, around 5.9 trillion miles. So 10,000 light years, which is just the rough distance to get above the main disk, is about 95 quadrillion kilometers. That is a 9 followed by 16 zeros in kilometers, or tens of quadrillions of miles. Human language does not have a normal word for that. It is just astronomically huge. Now connect that to real spacecraft speeds. The Parker Solar Probe, our current speed champion, reaches around 200 kilometers per second, about 450,000 miles per hour, when it dives close to the Sun. That is incredibly fast by our usual standards. It makes Earth orbital speeds look slow. But at that speed, to cover 10,000 light years, you are looking at on the order of 15 billion years of travel. That is longer than the age of the universe, which is about 13.8 billion years. So with technology anything like what we have now, you do not just struggle to leave the galaxy, you simply never arrive. So you push the thought experiment further, you allow yourself a science fiction engine. Say your ship can cruise at 10% of the speed of light, about 30,000 kilometers per second, around 18,600 miles per second. In real engineering terms, that is insanely hard, but let's grant it. Now that 10,000 light-year climb out of the disk takes roughly 100,000 years of ship time, not billions, but still, 100,000 years. If you want to go 100,000 light years to truly get beyond most of the galaxy's mass, now you are talking about 1,000,000 years of travel at that same speed. Maybe you try to go even faster, something like 90% of light speed. At that point, relativity starts to play a real role. Time dilation means that, from your point of view on the ship, the outside universe's clocks run slower. The people watching from the Milky Way might see hundreds of thousands of years pass while you cross tens of thousands of light years, but on your ship, maybe you only experience tens of thousands of years. That is a real effect. But notice, it doesn't save you from the basic issue. You are still dealing with durations far beyond any normal human lifetime, far beyond any current idea of a continuous mission. This is where the first serious red flag appears. Before black holes, before neutron stars, before gamma-ray bursts, the simple size of the Milky Way already forces you into timescales that your biology cannot handle. A healthy human today might live 80 years, maybe 100 with good medicine, maybe a bit more in some future scenario. But even if you stack lifetimes back to back, you are nowhere close to 100,000 years, or 1,000,000 years. So if you, as a normal human, try to leave the galaxy, the thing that gets you first is simple. You die of old age long before the galaxy even looks different. And this is the quiet, vicious part of the story. Distance and time are not dramatic, but they are relentless. The moment you decide to escape the Milky Way, you lock yourself into a fight against travel times that dwarf everything humans have ever done. All the other threats, radiation, dust impacts, life support failures, social breakdown, have to be survived not for a few years, but for tens of thousands of years, maybe more. You do not have to survive one dangerous event. You have to survive continuous risk, over absurd durations. So even before we talk about the wild stuff, you can see the outline of the real answer. The Milky Way does not need some sharp killer edge to stop you. It just buries you in distance. If you keep a normal human body, with a normal human lifespan, the first thing that kills you on a serious attempt to leave the galaxy is not the galaxy at all. It is time, working through your own biology. You simply run out of life, long before you run out of Milky Way. But maybe you say, fine, we will accept that. We will send multiple generations. Or we will upload mines or freeze people. Or do some other extreme trick. Let's say you somehow get past the aging problem for individuals. Then a new question hits you. If time and distance are the background boss, what is the first direct physical thing that actually tries to kill you the moment you start the trip? Before you even get clear of the solar system? Is it radiation from the sun? Is it cosmic rays? Is it dark matter? No. The first serious killer is much closer to home. It is the thing you ride on, the machine you absolutely need just to get moving at all. Before the galaxy has any chance to hurt you, your own rocket is already loaded with enough energy to wipe you out. How do you actually push a ship to a big chunk of light speed without killing yourself before you leave the neighborhood? To even start a serious attempt to leave the Milky Way, you need one thing first: speed, and a lot of it. In rocketry, that change in speed has a name: delta V. If you want to cruise at 10% of light speed, you're aiming for about 30,000 kilometers per second, around 18,600 miles per second. That is your target. Delta 5, the speed you want to gain, not relative to your launch pad, but relative to the surrounding space. Now compare that to what we actually do today. A really good chemical rocket, like the ones that launch satellites or crew capsules, can give you roughly 10 kilometers per second of delta V, maybe a bit more with careful staging. That's about 22,000 miles per hour. It sounds fast, but it's 3,000 times smaller than what you need for 0.1 C. Nuclear thermal rockets, which heat hydrogen with a nuclear reactor, might push that higher, maybe to a few tens of kilometers per second. Fusion or antimatter concepts, the really wild stuff, might nibble into the hundreds or maybe low thousands of kilometers per second on paper. But you're still staring at a gap of orders of magnitude. Here is where the rocket equation starts to crush you. The amount of propellant you need does not increase in a straight line with your target speed. It grows exponentially. Every extra bit of delta V costs you a larger and larger fraction of your total mass in fuel. So if you want to reach a serious fraction of light speed with a rocket that throws mass out the back, Your ship stops looking like a sleek star cruiser and starts looking like a skyscraper-sized fuel tank with a tiny HAB module pinned on top. Most of your ship is propellant, not people or life support. You are basically building a controlled bomb and then sitting right on it. And that is only half the problem, because all that fuel is not just mass, it is stored energy. Kinetic energy, the energy of motion, grows with the mass of your ship and with the square of its speed. That means if you double your speed, your kinetic energy doesn't just double, it goes up by a factor of 4. At relativistic speeds, that gets brutal very fast. Take a really small example, a payload of just 1 metric ton, about the mass of a small car, around 1,000 kilograms. Push that tiny mass to 10% of light speed. The energy you've given it is on the order of hundreds of trillions of joules. To make that more concrete, 1 megaton-class nuclear bomb releases a few quadrillion joules. So, just that 1 ton payload at 0.1 C carries the energy of over 100 megatons of TNT. That's more than the biggest nuclear devices ever tested on Earth. And that is just the payload, not the engines, not the tanks, not the rest of the ship. Now scale that up to a realistic crewed starship. You're not talking about 1 ton, you're talking thousands of tons for structure, shielding, fuel, food, habitats and machinery. Multiply that tiny car example by 1,000, and suddenly the kinetic energy of your ship is in the range of thousands of megatons. Think thousands of the largest nukes humanity has ever built, all effectively stored in one object, your vehicle. Whether that energy sits in your fuel, your magnetic fields, your fusion plasma, or your motion, it is there. And if something goes wrong, it comes out violently. So you have 2 giant issues now. You need insane delta V, which demands absurd amounts of propellant, and you're loading your ship with energy levels that make nuclear arsenals look small. But there's another constraint you cannot ignore: your body. You can't just jump from 0 to 0.1 C in a few minutes or even a few hours without crushing the crew. Humans can tolerate high acceleration for short bursts, but it's rough. Around 4 to 6 G, 4 to 6 times Earth's gravity, you start to grey out, you lose vision. Your body struggles to keep blood in your brain. Fighter pilots deal with this by wearing G-suits and using special breathing and body position techniques, and even then they can only hold that for seconds. For long-term comfort and safety, you really want to stay near 1 high, about 9.8 meters per second squared, which is what you feel standing on Earth. At 1 G, your speed builds up steadily. Keep that thrust on, and in just under a year of constant acceleration, you'd reach roughly 10% of light speed. That's 1 continuous year of being pushed back in your seat with Earth-like gravity just to speed up. Then you'd need another similar period at the end of your trip, flipping the ship around and thrusting the other way to slow down. Unless you want to slam into your destination at a fraction of light speed, which is another way to die. So even with a very human-friendly 1G profile, you're committing to multi-year engine burns just to handle the speed changes at the start and end. You could try to crank the acceleration up to 2G or more, cut those times in half and get to cruise speed faster. But now you're doubling the stress on every part of your body, on every bolt and weld and tank in the spacecraft. Human hearts, bones and blood vessels are not designed for years of 2G. Structures that were fine at 1G might start to fail. In practice, if you try to push too hard on acceleration to save time, the first things that give out are probably not stars or galaxies, but your own tissues, or your ship's frame. All of this sits on top of one more ugly fact. Rockets already fail a lot, and that's at the tiny energy levels we use now. We have seen chemical launch vehicles explode on ascent, releasing energy equivalent to tons of TNT, just from ordinary rocket fuel, and that's launching a few tens of tons to orbit, at maybe 8 or 10 kilometers per second, not pushing thousands of tons to a serious fraction of light speed. Now replace chemical propellant with fusion fuel, or antimatter, or gigantic laser beams hitting a sail. Because those are the kinds of systems you start to need for galactic scale travel. You are dealing with magnetic bottles holding ultra-hot plasma, or traps holding antimatter that will annihilate on contact with normal matter. or beams that focus enormous power on a thin film in front of you. Any instability, any containment loss, any software bug that misfires the system, and you don't get a heroic journey out of the galaxy. You get something that is basically a tiny artificial supernova right next to your crew. So when you step back and look at the whole picture, the first really credible killer in any attempt to leave the Milky Way is boring and brutal. It's your own propulsion. The delta V you need forces you to build a ship that is mostly fuel. The energy required turns that fuel into a colossal bomb. The acceleration profile pushes your body and your structure to their limits, and the track record of rockets tells you they blow up more often than you'd like, even at much lower energies, long before dark matter, black holes, or distant supernovae can do anything to you. There is a very real chance that your starship just destroys itself somewhere between low Earth orbit and the outer solar system. But let's say you somehow beat those odds. Your miracle engine works, your tanks don't rupture, your antimatter stays in its trap, and you manage to ramp up to cruise speed without turning the crew into paste. You are now leaving the immediate neighbourhood of Earth for real. The question becomes, once your own rocket decides not to kill you, what is the very next thing that starts quietly trying to finish the job, even before you're anywhere near interstellar space? To answer that, you have to look at the invisible shield you're about to fly out of, and what happens the moment you leave it. Why does stepping a little farther from Earth suddenly make the whole universe more dangerous to your body? The moment you decide to really leave home, not just go to low Earth orbit, you run into a problem you never had to think about on the ground. Radiation that has been mostly blocked for you your entire life. Earth is not just a rock with air, it's wrapped in a giant invisible shield, and the second you move beyond that shield, the rules change. Right now you live under a planetary scale radiation filter. Earth has a magnetic field, generated by moving metal in its core, and that field reaches far out into space. Charged particles from the sun, the solar wind, try to slam into us all the time, but most of them get steered around the planet. The field lines guide many particles down toward the poles, which is why auroras happen there, and they push the bulk of the solar wind away, forming a structure called the magnetosphere. On the day side, facing the sun, this bubble is compressed to tens of thousands of kilometers from Earth. On the night side, it stretches out into a long tail, more than 1 million kilometers, hundreds of thousands of miles. As long as you stay inside this magnetic bubble, the radiation environment is harsh compared to the ground, but still manageable. If that magnetosphere disappeared overnight, the particle flux on the surface would jump. High-energy protons and electrons from the sun and from deep space would hit the atmosphere directly, creating more secondary radiation that reaches the ground. Your annual dose would climb. Electronics in orbit would fail more often. For you, personally, this field is the difference between a planet that's comfortably habitable on the surface and a planet where life has to be much more shielded. Inside that bubble, though, there are regions that are actually worse, trapped pockets of charged particles called the Van Allen belts. These are donut-shaped zones where the magnetic field locks in high-energy protons and electrons. If you fly through the core of those belts slowly, the radiation dose can spike to many millisieverts per hour. A millisievert is a unit we use to track biological effect from radiation, not just raw energy. And a few tens of millisieverts in a short time is already something space agencies track carefully. Apollo astronauts had to cross these belts to get to the moon. They did not fry on the way, because mission planners intentionally aimed for trajectories that skimmed the less intense regions, and they passed through quickly, in hours, not days. When you add up their total radiation dose from the belts plus the rest of the trip, many of them got a few millisieverts to a few tens of millisieverts over the whole mission. That's roughly in the range of several CT scans on Earth. For a galaxy-bound mission, you would plan the same approach, punch through fast, minimize time in the worst zones, take the hit and keep going. Low Earth orbit, where the International Space Station flies, sits just under the inner part of this whole radiation structure. At about 400 kilometers altitude, around 250 miles, ISS crew are still well inside the magnetosphere, but they see more radiation than you do on the ground. Over a 6-month stay, an astronaut on the station usually gets somewhere around 80 to 160 millisieverts. That's several times the average yearly background dose a person gets on Earth, but still within what agencies consider acceptable career limits, especially when spread over time. Once you go beyond low Earth orbit, past the belts and out toward the moon or farther, the situation changes. You are still partly inside the magnetosphere for a while, but the shielding effect drops, and eventually, when you reach true interplanetary space, you are mostly at the mercy of whatever the Sun and the galaxy send your way. Measurements from spacecraft and from the Curiosity rover during its cruise to Mars show typical dose rates in deep space of about 1 to 2 millisieverts per day. So if you stay out there unshielded for a week, that's 7 to 14 millisieverts. A month, maybe 30 to 60. People often compare that to medical imaging. That is roughly like getting a chest CT scan every few days, over and over. Those numbers alone don't drop you on the floor. A single sievert, 1,000 millisieverts, in one shot is already serious. And a few sieverts in a short time can be life-threatening. What we're talking about here early in your trip is more subtle. It's a steady drip of extra dose that your body did not evolve to handle. Each high-energy particle that passes through you has a chance to break DNA, damage a cell, or trigger a mutation. Your body repairs a lot of that, but not all of it. Over months and years, those small hits add up. So as soon as you cross out of Earth's magnetic bubble, the clock starts on a slow kind of damage. Cancer risk goes up. The odds of cataracts in your eyes climb. Blood vessels, the heart, and the brain may suffer long-term effects. For a short mission, like a Mars trip, space agencies treat this as an elevated but acceptable risk. For a mission that is supposed to last tens of thousands of years, this background is not background anymore. It is a constant pressure on every cell of every crew member, and if you plan generations on board, on every child born there. On its own, this won't be the very first thing that kills you on a galaxy escape attempt. You probably won't collapse from radiation sickness in the first few days just from crossing the belts and leaving the magnetosphere. But that is exactly why it is so dangerous in the long run, because it's easy to ignore. It's not a single dramatic event. It's a health bar that starts very slowly draining the moment you leave Earth's protection. And everything else that tries to kill you in space, every solar flare, every cosmic ray, every design flaw, arrives on top of this constant low-level biological stress. And we haven't even talked about the spikes yet. So far, we only dealt with the average background, the steady drizzle of particles. Once you are outside Earth's shield, there is something much more violent that can hit you with almost no warning. Something that can turn that gentle radiation drip into a lethal blast in a matter of hours. It's not out in deep space. It's not from another galaxy. It's coming from the same star that has been keeping you alive your whole life. Next, you have to deal with the sun when it stops acting calm and starts firing. You just left Earth's magnetic bubble, and suddenly the calm yellow star you grew up with turns into a real threat. The steady background radiation is already eating into your long-term health, but there's something much more dangerous riding on top of that. Short, violent bursts from the sun itself. If your rocket was the first thing that could blow you up, the sun is the first thing that can quietly cook you from the inside out. The sun is not stable in the way your eyes suggest. Its surface and magnetic field are constantly shifting. Sometimes those magnetic fields snap and reconnect, and when that happens, the sun throws a tantrum. That tantrum is a solar flare, often paired with a coronal mass ejection, or CME. In a flare, the sun releases a burst of radiation, from radio waves all the way up to X-rays. In a CME, it hurls a huge bubble of plasma, charged particles, out into the solar system at speeds of hundreds to thousands of kilometers per second. That's hundreds of thousands to a few million miles per hour. The strongest of these, the X-class flares, sit at the top of the solar flare scale. An extreme X-class event can dump something like 10 million billion joules of energy into space. That's the kind of number where comparisons start to fail, but it's in the rough zone of billions of large nuclear weapons going off at once, spread out over the sun's surface and over time. We've seen these events with spacecraft like SOHO and SDO, which constantly watch the sun in different wavelengths. When one of these eruptions is aimed even partly at Earth, we see radio blackouts, GPS glitches, auroras pushed much closer to the equator, and sometimes power grid problems on the ground. Those visible effects are actually the mild side for you as a deep space traveler. The real problem is the wave of high-energy particles that often follows. The solar energetic particles, mostly protons, some heavier ions, moving at a significant fraction of light speed. Their energies can reach into the hundreds of mega-electron volts, high enough that they cut through thin metal and human tissue like bullets on the atomic scale. When one of these proton storms washes over a spacecraft, the radiation level outside can spike from that background 1 or 2 millisieverts per day to multiple sieverts in just a few hours. To see what that means in practical terms, remember the rough biology. A whole body dose of about 1 sievert in a short time will make many people sick, will raise long-term cancer risk, but most will survive. Around 4 to 5 sieverts, absorbed quickly, you are in the zone where about half of unprotected humans will die within weeks, even with medical care, from acute radiation sickness. Push that toward 8 or more, and survival without perfect treatment becomes very unlikely. A major solar proton event, hitting a lightly shielded crew module, can deliver several sieverts before you even finish a sleep cycle. So now you have a real sharp threat on top of the slow drip. It is not constant like the background. It is more like a space weather version of a hurricane. Most of the time, dose rates are elevated but manageable. A few times per solar cycle, over roughly 11 years, you get moderate storms that you can ride out with decent shielding. But a few times in centuries, at least based on historical data like the 1859 Carrington event, you can get a true monster. If one of those hits your ship when you're outside Earth's magnetosphere, and with weak shielding, the crew can receive lethal doses in less than a day. You might think, fine, we'll just put thick walls around us. That is the correct instinct, but it clashes directly with everything you did in the last section to make your rocket possible. To stop or at least greatly reduce these proton storms, you want material that's good at slowing and scattering charged particles. Hydrogen-rich materials work well, things like water, polyethylene, or other plastics, because they cause the protons to lose energy gradually, instead of making showers of more dangerous secondary radiation like heavy metals can. The problem, as always, is mass. Every extra ton of shielding you add means more propellant, more engine power, and a bigger, more dangerous energy budget. For a trip to Mars, current concepts talk about building a small storm shelter, a cramped, heavily shielded compartment inside the ship where the crew can stay during a big solar event, maybe for a day or two. You don't shield the whole spacecraft to that level, it's too heavy, you just shield a small safe room. Now stretch your mission from a few years to tens of thousands of years. Your galaxy-leaving ship needs that sort of protection, not for 1 or 2 events, not for a handful of storms over a decade, but for hundreds, maybe thousands of major flares over its lifetime. The sun will keep cycling, throwing out eruptions, long after the original crew are dust. That means your storm shelter has to stay structurally sound, correctly designed and properly used, for longer than all of recorded human history so far, multiplied many times. And if you cut corners to save mass and energy, you raise the odds that, sooner or later, one unlucky storm arrives when your systems are down, your sensors misread data, or your crew simply make a bad call. There's another twist. As you move farther from the sun, the intensity of its light and of many lower energy particles drops with distance. But the most dangerous solar energetic particles can still hit you over huge volumes of the solar system. Space is big, but these events don't care. They spread along magnetic field lines and across large regions. And by the time you're truly in interstellar space, far from the sun, it's not solar storms you worry about anymore, it's galactic cosmic rays. So the window where the sun is your worst radiation enemy is early. In the first segment of your journey, exactly when you're still trying to get up to speed and shake off Earth's gravity. That's the dark irony here. The same star that powered the chemistry that built your body, that fed your planet for billions of years, becomes one of the most acute threats as soon as you step outside its protective bubble. A single extreme X-class flare, paired with a proton storm, hitting your ship when you're just beyond Earth's magnetic shield, maybe before you're even a light day away, can quietly end your mission in less than 24 hours. Your trajectory is still barely out of the inner solar system, but the crew are already dying from internal radiation damage. If you're asking, what can kill me in the first week of trying to leave the Milky Way, even if my rocket worked? This is a prime candidate. One bad solar event, poor shielding, and bad timing. And you never even make it past the edge of the sun's influence. But suppose you get lucky. Your engines hold, your storm shelter works, you time your launch during a quieter phase of the solar cycle, and you ride out the flares that do happen. You keep thrusting. After a while, the sun's magnetic bubble itself starts to thin out around you. You're about to cross another invisible border, farther out than any human spacecraft has gone, into a region where the sun stops being the main source of radiation, and the entire galaxy takes over. Out there, the threat is not sudden spikes from one star. It's a constant universal firing squad of particles coming from every direction at once. What happens when the sun's protection finally runs out, and you're not just outside Earth's shield, but outside the solar system's shield too? Up to now, the sun has been both a threat and a kind of guardian. Its magnetic field and solar wind carve out a bubble around us that softens some of the worst radiation from the rest of the galaxy. Once you cross that outer boundary, the heliopause, you leave the sun's turf and step into the galaxy's raw environment. That's where the background radiation stops being a drizzle and turns into a real firing squad. The sun constantly blows out a stream of charged particles, the solar wind. That wind pushes against the thin gas between the stars, the interstellar medium, and inflates a bubble called the heliosphere. Inside that bubble, solar particles dominate a lot of the local space weather. At the edge, the pressure from the solar wind and the pressure from the interstellar medium balance out. That rough border is the heliopause. It's not a solid wall, it's a fuzzy region, but it sits at around 120 astronomical units from the sun, give or take. 1 astronomical unit is the distance from Earth to the sun, so 120 astronomical units is about 18 billion kilometers, around 11 billion miles. 2 spacecraft have actually crossed this line, Voyager 1 and Voyager 2. They were launched in the 1970s, flew past the giant planets, and then just kept going. In the 2000s, their particle detectors saw something dramatic. The flux of lower energy solar particles dropped sharply, while the flux of much higher energy particles from outside the solar system, galactic cosmic rays, jumped up. That was our first direct proof that the heliosphere really is a bubble in the galaxy, with a different radiation environment inside and outside. So what exactly are these galactic cosmic rays that start dominating once you're out there? They're not rays in the sense of light beams, they're particles, mostly protons, some alpha particles, which are helium nuclei, and a smaller fraction of heavier atomic nuclei, like carbon, oxygen, or even iron. They're accelerated by violent events in the galaxy, like shockwaves from supernova explosions, and possibly other extreme objects like pulsars and black hole jets. The key point is their energy. Many carry energies in the range of billions to trillions of electron volts. For comparison, a typical medical X-ray photon is in the tens of thousands of electron volts. These things are orders of magnitude more energetic. At those energies, each cosmic ray particle is like a microscopic projectile moving at close to light speed. When one slams into your spacecraft, it can punch through layers of material, knock atoms out of place, and create whole showers of secondary particles. When it passes through a human body, it leaves a track of ionization, tearing through DNA and cellular structures. It doesn't feel like anything, you don't get a zap, but statistically, each hit adds to the damage. We already have some numbers for what this means in practice, even inside the heliosphere. Based on measurements and models, NASA estimates that an astronaut on a multi-year deep space mission, say a round trip to Mars with current shielding concepts, might receive something like half a sievert to 1 sievert in total. That's enough to significantly raise lifetime cancer risk and cause other long-term health issues, but it's in a range agencies are at least willing to consider for rare missions. Outside the heliosphere, the Voyagers show that the intensity of galactic cosmic rays is higher again. The sun's magnetic field and solar wind used to deflect some of those rays before they ever reached the inner system. Once you're past the heliopause, that extra protection is mostly gone. So take that 0.5 to 1 sievert over a few years as a baseline for inner system deep space, then assume a higher rate outside. Now stretch your trip from a few years to tens of thousands of years. Even if you have good shielding, the integrated dose each person would receive over that timescale doesn't just push up their cancer risk. It basically guarantees that their DNA is going to be shredded statistically. And if you're running a generational ship, the problem is worse. You're not just keeping one person alive for 20 years, you're trying to keep a population's genetics stable across thousands of years of constant high-energy bombardment. The reason this threat is different from the solar flares you just dodged is simple. Flares are spikes. Cosmic rays are a constant background. When the sun throws a major flare, you can see it, get a warning, dive into a storm shelter, and wait a day. The event rises, peaks, and fades. With galactic cosmic rays, there is no off switch. The flux is always there, from every direction, and it doesn't care about your schedule. You can try to reduce it, but you can't ever make it go away completely. On top of that, cosmic rays are harder to stop. Lower energy solar protons can be blocked fairly well with tens of centimeters of water or plastic. High energy heavy ions from outside the heliosphere can plow through meters of material and still cause damage. And when they hit dense shielding, they can actually create secondary particles that spread the energy around. So you face a nasty trade-off. Thin shielding lets more primaries through. Very thick shielding stops more primaries, but can generate showers inside the material. Engineers try to design smart combinations of thickness and material type to minimize overall dose, but there is no perfect wall. And it's not just the crew that takes the beating. Every system on the ship is under fire. Electronics suffer from bit flips, where a single cosmic ray changes a 1 to a 0 in memory, and from cumulative damage that can eventually ruin components. Materials can become brittle or change properties under long-term radiation. Sensors slowly degrade. Over years, you can plan for maintenance, swap parts, reboot systems. Over tens of thousands of years, you are asking every wire, chip, and circuit board to survive a level of total exposure that we simply do not build for today. So galactic cosmic rays are not going to kill you in a single dramatic burst like a huge solar flare. They are the slow, grinding enemy that never sleeps. They eat at your hardware, your software, and your biology non-stop. In a realistic galaxy escape mission, even if you avoid every big disaster, even if no major flare or engine failure ever hits you, these particles alone are enough to make long-term survival incredibly unlikely, without ridiculous amounts of shielding mass, or completely different kinds of bodies, like heavily modified or digital minds. And remember, up to now, we've mostly talked about radiation. We haven't even hit the other big problem that comes with moving at a serious fraction of light speed through even very thin gas and dust. Because once you're out past the heliosphere, cruising at, say, 0.1 C, there's something else waiting for you. The space between stars is not perfectly empty. And at those speeds, tiny bits of matter stop being harmless specks and start behaving more like weapons. If a single grain of dust can carry the energy of a bomb when it hits your hull, what does that do to a ship that has to survive millions or billions of kilometers of that environment? You might think that once you get far from planets, moons, and asteroid belts, space finally becomes empty and safe. It doesn't. At 10% of light speed, even almost nothing turns into a real physical threat. The space between stars looks like a perfect vacuum, but to your ship, moving that fast, it's more like a very thin minefield stretched over light years. Between stars, the average density of normal matter is about 1 hydrogen atom per cubic centimetre. That's 1 atom in a sugar cube-sized volume, which sounds like nothing. In a lab on Earth, that would count as an extremely good vacuum. Mixed into that are trace amounts of heavier atoms and tiny dust grains, fragments of carbon, silicates, ice, and other materials. Most of the volume is emptiness, but your ship isn't just sitting there. It's ploughing through this at a huge speed. Now scale the path you're travelling. You're not going a few hundred kilometres. On a serious attempt to leave the galaxy, you're talking about distances of trillions, quadrillions, or more kilometres. Even with that very low density, your ship's forward cross-section will sweep through an enormous total volume of space. That means, statistically, you will hit particles and dust grains. The gas-level stuff, mostly single atoms, will add up to drag, heating, and extra radiation over long times, but the real concern is the rare, slightly larger grains. You don't need to hit them often. At 0.1 C, even one can be enough. So how bad is a single tiny grain really if you're moving at 10% of light speed? Take a dust grain with a mass of about 1 milligram. That's 1,000th of a gram. About the weight of a speck of sand or dust you'd brush off your sleeve without noticing. The kinetic energy of a moving object depends on its mass and the square of its speed. When you plug in that tiny mass and a speed of roughly 30,000 kilometers per second, about 18,600 miles per second, the number you get for energy is huge. Hundreds of millions of joules. To make that feel real, think about explosives. Roughly speaking, that kind of energy is similar to what you'd get from detonating more than 100 kilograms of TNT, well over 200 pounds all at once. So that single, invisible grain of dust, if it hits your hull head-on at 0.1 C, does not make a scratch, it makes a local explosion. It vaporizes itself, vaporizes part of your shield, and sends a cone of super-hot plasma and shockwaves ripping into whatever is behind that point. And that was just 1 milligram. Larger grains exist. Even smaller ones, at these speeds, are dangerous. At 0.1 C, you have turned the interstellar medium into a stream of microscopic projectiles, each with explosive levels of energy relative to your ship. The faster you go, the worse it gets because the energy rises with the square of speed. Double the speed, quadruple the energy per impact. You might think this is all just theory, but we've already seen what tiny particles can do at much lower speeds, right in Earth orbit. The International Space Station orbits at about 7.7 kilometers per second, around 17,200 miles per hour. That is less than 0.003% of light speed, tiny compared to 0.1 C. Even so, micrometeoroids and space debris have hit the ISS over and over. They have punched pits into windows, cratered exposed metal handrails and panels, and pierced experiment covers. Flux measurements show that the station is hit by detectable micrometeoroids and artificial debris regularly. Now compare the speeds. Your Starship at 0.1 C is moving about 4,000 times faster than the ISS. Because impact energy goes as speed squared, that's roughly 16 million times more energy in an impact for the same mass. A grain of dust that would barely mark a surface at ISS speed becomes a serious threat at 0.1 C. The kind of tiny debris that today just makes small pits in station windows would, at your speed, blow holes through shielding, rupture lines, and potentially breach pressure hulls. Even if the majority of grains you hit are smaller than a milligram, the cumulative effect over millions or billions of kilometers is erosion. Your forward surfaces will slowly ablate, wearing away as a constant hail of microscopic impacts strips material off. Any sensor, antenna, or delicate structure pointed even slightly forward will be sandblasted by ultra-high energy particles. Over years, that alone can degrade your ship. Over tens of thousands of years, it's catastrophic unless you design for it from day one. So how do you stop bullets you can't see, coming straight at you at relativistic speeds, from random directions within a narrow cone ahead of your motion? Engineers already have one basic idea for dealing with high-speed dust and micrometeoroids: layered shields. One common design is called a Whipple shield. You put a thin outer layer some distance away from the main hull. When a particle hits that first layer, it shatters and vaporizes, spreading out the energy and material. By the time the cloud reaches the main wall behind it, the impact is more distributed and less likely to punch a clean hole. For a spacecraft in low Earth orbit, a few millimeters of aluminum and a bit of spacing can be enough to stop most small pieces of debris. For a ship moving at 0.1 C, that is nowhere near enough. You would need a thick stack of sacrificial layers on the nose, maybe meters of material. Some concepts talk about carrying a huge block of ice or water in front as a shield, letting it slowly erode over time. Others add electromagnetic fields to deflect charged dust and ions before they hit. You can even imagine shooting a thin cloud of gas or plasma ahead of the ship to pre-vaporize incoming dust grains before they reach the main structure. But every one of those ideas runs into the same wall you've already seen: mass. A massive forward shield adds tons, maybe thousands of tons, to the nose of your craft. That mass has to be accelerated to 0.1 C, along with everything else. That loops you straight back to the earlier sections, to the rocket equation and the horrifying energy budget. More shield mass means more fuel, more powerful engines, more stored energy, and a bigger explosion risk if something goes wrong. On top of that, detection is hard. At those speeds, you don't get much warning. Even if you could detect a millimeter-sized grain ahead with radar or LiDAR, the time between detection and impact at a relative speed of tens of thousands of kilometers per second is tiny. You don't get to dodge, you just take the hit and hope your shield did its job. So if you really push into the 0.1 C range or beyond, unanticipated dust impacts quickly climb into the list of top killers. Not theoretical, not exotic. Just normal interstellar dust, amplified by your own speed, turning into random, high-energy strikes on your forward surfaces. One unlucky grain that's a bit larger than you designed for, hitting a slightly weaker spot in the shield, can end your mission in a fraction of a second. Long before the Milky Way's star density even begins to thin out around you. Up to this point, we've stacked threats. Your own rocket might explode, the sun might blast you, cosmic rays and dust might slowly or suddenly rip your ship apart. But notice something. Every single one of these problems hits you over time. You have to keep engines stable for years, dodge flares for years, survive radiation and erosion for years. That brings you back to the quiet, brutal background issue we started with. Even if you solve all of these engineering and physics problems, what do you do about the fact that a realistic trip to leave the galaxy takes tens of thousands to hundreds of thousands of years, while a human body is built for maybe 80? You can fight rockets, radiation, and dust with engineering. But how do you fight a clock that runs for 100,000 years? This is the part that most will just go really fast plans skip. Even if you solve propulsion, shielding, and navigation, the timescale of actually leaving the Milky Way makes a normal human lifetime look microscopic. Go back to the distances. Say you don't manage 0.1 C, you only manage 0.01 C. That's about 3,000 kilometers per second, around 1,860 miles per second. That is already way beyond anything we know how to build, but let's allow it. At that speed, to cross 10,000 light years, you're looking at roughly 1 million years of travel time on the ship's clock. 1 million years versus a human lifespan of maybe 80 years if things go well. You're off by a factor of about 10,000. Even if you hit the more optimistic 0.1 C, roughly 30,000 kilometers per second, about 18,600 miles per second, you only cut that to around 100,000 years to clear 10,000 light years. That is still 3 orders of magnitude longer than a human lifetime. So for any realistic leave the galactic disk goal, if you keep anything like a human body and a human lifespan, you will be dead a tiny fraction of the way into the journey. You don't see the halo, you don't see the edge. You just live and die inside the first microscopic slice of the mission. So then you might say, doesn't relativity help? Can't time dilation save the crew if they go fast enough? Relativity does help, but only if you push to speeds extremely close to light speed, much higher than 0.1 C. At about 0.99 C, 99% of light speed, the time dilation factor called gamma is around 7. That means that for every year you experience on the ship, about 7 years pass back in the galaxy's rest frame. That's real, it's not science fiction. But look at what you had to do to get that effect. You needed an engine that can push a massive ship to 0.99 C, not just 0.1 C. The energy cost doesn't just scale in a straight line with speed, it shoots up. You're in a regime where relativistic mass and kinetic energy are enormous. Then you have to accelerate up to that speed, coast, and decelerate without killing the crew with G-forces or blowing up the ship. Even if you accept all that and you get this nice big-time dilation factor, the numbers are still ugly. To cross 10,000 light years and have it feel like, say, 1,000 years on board, you still need a cruise speed extremely close to light speed and long stretches of coasting. 1,000 years of subjective time is shorter, but it's still 10 to 12 times the length of any human civilization so far. And time dilation doesn't make radiation, microgravity, and mechanical wear go away. From your point of view, your clock is slower compared to the outside, but on the ship, your body still ages according to your local time. You still take hits from cosmic rays, still lose bone in low gravity, still face system failures. All that changes is how much outside history passes while it happens. So you hit a hard conclusion. If you're using anything like current physics and normal biology, This is not your trip. It's not even your great-great-grandchildren's trip. It's a chain of generations so long you can't really picture it. That leads straight into the idea of a generational ship, a huge closed habitat where people are born, live and die, while the ship cruises between stars or out of the galaxy. On paper, that sounds like a solution. In reality, it multiplies your failure chances. Think about reliability in simple numbers. Suppose you design your ship to be incredibly robust. Every year, you say there's only a 1 in 100,000 chance, 0.001%, that some catastrophic failure happens that you can't fix, something that kills the mission. A reactor meltdown you can't contain, a major hull fracture you can't repair, a bioreactor collapse you can't recover from, or a social breakdown that destroys your technical base. A 1 in 100,000 annual risk sounds small. Over 10 years, the odds are still very low that you hit that failure. Over 100 years, it's still not huge, but stretch that same tiny yearly risk over 100,000 years. The chance that you never have a single mission-ending failure in all that time drops towards zero. It's like rolling a die with 100,000 faces once a year and hoping you never, ever roll the one bad number, not for 10 rolls, not for 1,000, but for 100,000. Sooner or later, you hit it. And that's just the raw engineering side. Add in biology and society. Humans forget things. Cultures change. Procedures drift. Old maintenance protocols get simplified, then ignored. Knowledge gets lost when people die. Systems get patched in quick, dirty ways to solve short-term problems. Even if the hardware stays perfect, the software in people's heads will not stay locked and stable for 100,000 years. You can write manuals, build training systems, automate as much as possible. But you are fighting entropy in hardware and in culture at the same time. This is why time itself becomes the quiet, undefendable threat. You can build armor against dust. You can set up shelters against flares. You can patch leaks, swap parts, and rewrite buggy software. But there is no simple shield, no single trick that lets a fragile, Earth-evolved biological species run a complex, closed spaceship civilization flawlessly for 100,000 years straight. Aging grinds down individual bodies. Entropy grinds down machines. Random bad luck hits you eventually. Over mission times on the scale of geological eras, the default outcome is not, we reach the edge of the galaxy. It's something, somewhere, finally goes wrong in a way we can't undo. So if you ask, in a cold, probability-driven way, what is the most likely thing to kill a biological crew on a real attempt to leave the Milky Way, even if we hand-wave incredible engines and good radiation shielding? The answer isn't a dramatic explosion or some exotic cosmic monster. It's time. Time makes every other risk almost certain. Time guarantees that small problems pile up. Time guarantees that people who started the journey are long dead before they see any outside. And that connects straight to the next problem. Because even before you get to century scale or 1,000-year scale issues, your body starts to fall apart in space almost immediately. You don't need 100,000 years for biology to become a problem. Microgravity and radiation start wrecking you in weeks and months. So the question becomes, even if you could somehow manage the big clock, how do you stop your own body from failing, starting on day one of the mission? The moment you leave Earth's gravity and stay gone, your body starts to fall apart. And it doesn't wait for decades to do it. The trip to leave the Milky Way sounds huge and distant, but your own biology starts failing on day one, long before you leave the solar system, long before you even reach another star. Start with your skeleton. On the ground, your bones are constantly loaded by 1 g of gravity. Every step you take, every time you stand up, your body is telling your bones, stay strong, stay dense. In microgravity, that signal basically disappears. On the International Space Station, where astronauts float at around 400 kilometers, 250 miles up, their bones start to lose density fast. Especially in the hips, spine and legs, the weight-bearing regions. Even with an aggressive workout schedule, about 1 to 2% of bone density melts away per month in those key areas. Over 6 months, that can add up to 10 to 12% loss. On Earth, losing that much bone density that quickly would get you flagged for serious osteoporosis. You'd be at higher risk of fractures and recovery would be slow and painful. Now stretch that out. You're not doing 6 months, you're doing years, maybe decades. in reduced gravity. Yes, you can spin parts of your ship to simulate gravity, but unless you build a huge rotating habitat, it's hard to get a clean, stable 1G without nasty side effects like motion sickness or weird gradients. Even a slightly lower artificial gravity, say half G or less, will probably still mean ongoing bone loss, just maybe at a slower rate. The older you are, the worse your body responds. And all of this is happening under a constant background of radiation, which also damages tissues and slows healing. So bones become brittle, fractures become more likely, and simple accidents, a bad fall in a rotating habitat, a hard impact during a maneuver, can turn into serious injuries. On Earth, you'd go to a hospital. On a starship 1,000 years from home with limited medical gear, a broken hip in a radiation-damaged body can easily be a life-ending event. Muscles follow the same path, and they do it even faster. Without gravity, your muscles aren't pushing against anything. The big groups in your legs, back and core weaken quickly. Astronauts in low Earth orbit already need more than 2 hours of intense exercise every single day, using treadmills with harnesses, resistance machines and bikes just to slow down the loss. Even with all that, they come back weaker, with less endurance and strength. Your cardiovascular system also detrains. In microgravity, blood doesn't pool in your legs. It shifts toward your chest and head. Your body responds by reducing total blood volume. Your heart, which doesn't have to pump as hard against gravity, slowly changes shape, becoming more spherical and less powerful. When ISS crew return to Earth after months, many of them struggle just to stand up and walk at 1G. They feel lightheaded, their muscles shake, their balance is off. Now take that and push it to the extreme case. People who are born and raised in low gravity on a ship. Their bones and muscles never fully develop for 1G. Their hearts and blood vessels adapt to a weaker load from the start. They might function fine inside the rotating habitat they grew up in, but the moment something goes wrong, a fire, a hull breach, a need to move heavy equipment, or a need to land on a planet with anything close to Earth gravity, they are in trouble. Physically, they may simply not be able to handle the load. In an emergency, that gets people killed. On top of mechanical wear and tear, there's the slow radiation hit. You started back in sections 3, 4 and 5. Deep space radiation, at something like 1 to 2 millisieverts per day, adds up fast. In a year, that's around 365 to 730 millisieverts. In 10 years, you're at several sieverts, even if you have decent but not perfect shielding. That dose range isn't instantly lethal if it's spread over time, but it pushes your lifetime cancer risk way up, and there's growing evidence that it also hits your circulatory system and your brain. So over decades, you're not just a bit more likely to get cancer, you're more likely to have heart problems, more likely to have strokes, more likely to have cognitive and memory issues. Your eyes take damage, increasing cataract risk. The immune system can be weakened. That's for adults who start healthy on Earth, then go up. Now extend that to children conceived and born in that environment. Their developing cells are more sensitive to radiation. DNA damage during growth can lead to structural birth defects, learning problems and higher cancer rates at younger ages. If your ship is a multi-generational ark, you are slowly turning your crew into a radiation-scarred population. Each generation inherits a bit more genetic damage unless you're constantly doing extremely advanced medical and genetic repair work, something far beyond what we can reliably do now. At some point, the ship's population stops being a tough, adaptable group and becomes fragile. Fertility might drop, miscarriages might rise, immune systems might be compromised. One bad outbreak of disease in that context can cut deep, because the baseline health of the average person is already damaged by microgravity and radiation. All of this leads to a simple, harsh point. Your entire biology is tuned to Earth. Your bones expect 1G of constant load. Your muscles expect gravity and ground reaction forces. Your circulation expects a column of blood from feet to head. Your DNA repair mechanisms evolved under a certain range of surface radiation, filtered by the atmosphere and magnetosphere. Your circadian rhythms are tied to a 24-hour day-night cycle driven by one particular star. The further you take that system away from its design environment, first into orbit, then into deep space, then out of the solar system, then across the galaxy, the more it turns from an asset into a liability. Every day in microgravity, every extra millisievert of radiation is pushing your cells and organs a little further away from what they were built to handle. You can fight back. You can build huge spinning habitats that simulate close to 1G. You can put meters of water and plastic around living areas to absorb radiation. You can design exercise programs, advanced medicine, even genetic engineering to harden people against this environment. But those solutions all cost mass, energy, and constant maintenance. And remember, your mission isn't survive for 6 months. It's survive for tens of thousands of years. So if you try to leave the Milky Way with ordinary human bodies, and you don't go all in on massive gravity habitats and extreme radiation shielding, the thing that quietly kills your species first is not some dramatic alien hazard. It's the simple fact that you were never meant to live in deep space at all. Your bones, your muscles, your blood, your DNA, they were all built for Earth. And they start failing almost immediately once you leave it behind. And your body isn't the only complex, delicate system you're hauling into the void. You also need a full, working ecosystem on that ship. Something that can feed you, give you air, recycle your waste, and stay balanced for longer than any ecosystem on Earth has ever been closed off. So the next question is, even if your bodies somehow hold together, can the little artificial Earth inside your ship stay alive without collapsing on you? You've seen what space does to your body, but your body is only one part of the problem. The other part is everything that has to keep you alive. Air, water, food, and waste recycling. On Earth, a whole planet does that for you, for free. On a starship trying to leave the galaxy, you have to build a tiny, fake planet inside a metal tube. And it has to work not for months, but for thousands of years. That's not just hard. It might be the single most fragile part of the entire mission. Look at how we do it now. The International Space Station looks advanced, but in ecological terms, it's primitive. It is not a closed system. Cargo ships bring water, food, air tanks, nitrogen, spare parts, tools, electronics, pretty much everything. The station does some recycling. It scrubs carbon dioxide from the air. It recovers some water from humidity and urine, but it still needs a steady stream of deliveries from Earth to function. If you cut those supply lines, the ISS would run out of key materials pretty quickly. It would lose nitrogen from slow leaks. It would run short of certain trace elements. Its filters would clog with no replacements. The crew would run out of packaged food. In other words, our best long-term human habitat in space right now survives because Earth is a few hundred kilometers away, and we can send up cargo every few months. Your galaxy-leaving ship will not have that luxury. No one is sending a resupply craft to you when you're a few light days, or light years, or thousands of light years away. Every atom that matters to life on that ship has to be caught, cleaned and reused over and over. Nitrogen for proteins and air, phosphorus for DNA and cell membranes, potassium, iron, zinc, iodine, even rare trace metals that enzymes use in tiny amounts. You don't get to throw anything away. Leaks aren't just annoying, they are permanent losses you can't replace. We have already tried something a little like this on Earth, and it did not go smoothly. In the 1990s, there was an experiment called Biosphere 2. The idea was simple on paper. Seal 8 people inside a closed 3.1-acre glass and steel structure in Arizona, with soil, plants, small animals and oceans, and see if they could live for 2 years without outside input. In practice, the system went out of balance fast. Carbon dioxide levels rose way beyond expectations. Oxygen levels dropped so much that the crew started to have trouble with basic tasks. They eventually had to add oxygen from outside to keep people healthy. Some insect species died out. Others, like ants and cockroaches, boomed. Microbes in the soil behaved in ways planners did not predict, locking up carbon or nutrients differently. All of this happened with real-time support from Earth, with scientists watching, with replacement parts and with the ability to open the door if things went bad. That experiment was on a fixed, solid planet, under full gravity, with easy access to outside help. It still showed that even a large, carefully planned artificial ecosystem can drift into dangerous territory in less than a year. Air chemistry moved out of the safe zone. The balance of species shifted. Human health started to suffer. Now scale that problem to a starship. On board, you need far more than just a hydroponic rack of lettuce. Long-term survival means you need a full food web, or a very advanced technological replacement, plants to make oxygen and food, microbes in soil, or bioreactors to break down waste and recycle nutrients, possibly insects or fish, or other animals for protein and for pollination. Complex cycles of carbon, nitrogen, phosphorus, sulfur, and trace elements have to run smoothly without killing off key species or letting any one population explode. You can try to do it all with machines and chemicals, but then the complexity just moves into your hardware. Pumps, filters, membranes, reactors, sensors all have to stay running and calibrated for thousands of years. Filters clog, membranes wear out, sensors drift. Software has bugs, humans make mistakes when they repair things. Small errors in one loop can build up quietly and then suddenly push the whole system past some tipping point. And if you go the more natural route, with soil and living ecosystems, you inherit all the complexity of nature, squeezed into a much smaller, much more fragile space. A minor shortage of one micronutrient, like zinc or iodine, might not kill crops, but it can damage human health over years. People can have enough calories but still suffer from hidden hunger, deficiencies that weaken their immune systems and stunt growth. On a timescale of 10 or 20 years, you might be able to manage this actively. You measure everything, correct imbalances, tweak farming, adjust air chemistry, add or remove species in small ways. On a timescale of thousands of years, the odds that everything stays just right without any runaway feedbacks drop hard. One new fungus that evolves in your hydroponic lines, one virus that hits your staple crop, one key insect pollinator that slowly goes extinct in your ship's artificial light and temperature cycles. Any of those can cascade into food shortages, air issues, or toxic buildups. This is where a very realistic first killer can appear, long before black holes or supernovae ever matter to you. The failure doesn't look cinematic. It looks like crops slowly yielding less and less. It looks like an algae bioreactor that starts growing the wrong microbe, releasing toxins instead of oxygen. It looks like carbon dioxide levels that creep up year by year because a small leak in a scrubber went unnoticed and the repair parts are poor quality. People are tired, systems are old, monitoring equipment is starting to fail. You end up with a slow drift in ecosystem chemistry that no one fully understands anymore. Maybe the original experts are long dead. Maybe the training got watered down over generations. People learn enough to operate the system day to day, but not enough to see deep imbalances forming. Then you start to see the biological signals. Babies born a bit smaller on average, more miscarriages, old people dying earlier, weird clusters of disease, chronic fatigue, mental health breaks. By the time the crew realizes that something is seriously wrong with their life support and food web, they might not have the tools or the knowledge to fix it. They're surrounded by machinery and grow rooms and tanks that look like they work, but the chemistry is off by just enough to be fatal over decades. The outside universe doesn't have to do anything. No asteroid impact, no gamma ray burst, no alien attack. Your own attempt to copy Earth in a box fails slowly and takes you down with it. This is why, in any honest risk list for a galaxy-leaving ship, ecological collapse sits near the top. It is not as flashy as a rocket explosion, but it is much more likely over long spans of time. Starvation is simple. If crops fail, you die. Suffocation is simple. If oxygen production and carbon dioxide removal fall out of balance, you pass out and don't wake up. Poisoning is simple. If some waste product builds up in the air or water beyond what your systems can handle, the crew gets sick and starts dropping. And remember, this is all stacked on top of everything you've already heard. Radiation, microgravity damage, dust impacts, propulsion risks, timescales. Each one on its own is hard. Combined, they multiply. A crew weakened by radiation and bone loss is more vulnerable to a food crash. A maintenance team worn down by generations of work is more likely to miss a key warning sign. A strained ecosystem is less able to absorb small shocks, like a minor equipment failure or a short-term power loss. So if you want a realistic answer to what actually kills you first if you seriously try to leave the Milky Way, you don't have to reach for exotic physics. You just have to look at your greenhouse and your air filters. Because long before you get near the galaxy's edge, Your biggest threat might be that your little artificial Earth stops working, and you slowly run out of what matters most: breathable air and reliable food. But even if you somehow keep your tiny world stable, there's still the much larger world around you, the galaxy itself. You won't be alone out there. You'll be moving through neighborhoods of stars, some quiet, some violent, over tens of thousands of light years. So next you have to ask, while your ship is fighting to stay alive inside, what can the stars themselves throw at you from the outside? You've handled your own ship, your own biology, and your own mini ecosystem. But you're not flying through an empty void. You're flying through a moving, shifting crowd of stars. On human scales, space looks empty. On galactic scales, it's busy. And over a 10,000 light-year route, you're threading your way through a lot of potential trouble. Near the Sun, the closest star, Proxima Centauri, is about 4.2 light-years away. That sounds huge. And for today's probes, it is. But on a map of the Milky Way, that's tight packing. In our region, stars are typically just a few light-years apart. Now stretch your journey, not 4 light-years, but 10,000. Your path crosses through region after region, each with dozens or hundreds of stars scattered around you. You can, in principle, plan a path that stays well away from anything bright or violent. You're not randomly drifting. You have engines, guidance, and long-range surveys. But well away has to stay true for millennia. Tiny errors in navigation, tiny changes in course to dodge dust or adjust for fuel use, all of that accumulates. Over a trip that lasts tens of thousands of years, a small deviation can put you a lot closer to a star than you meant to be. If you pass within just a few astronomical units of a star, you're in trouble. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, around 93 million miles. Inside that kind of radius around a star, you're diving into its radiation and particle wind. For a quiet, sun-like star, that means intense light, heat, solar wind, and the chance of getting hit by flares and coronal mass ejections that are far stronger than what you saw near Earth. For a red dwarf, it can be worse. Many red dwarfs are hyperactive, with flares that can increase their brightness dozens of times in minutes. If your ship cuts too close, their particle storms and high-energy light can hammer your shielding and your crew. Now think about using stars for gravitational slingshots. It's tempting. A close pass can bend your path and trade gravitational potential energy for speed, saving fuel. We already do mild versions of this with planets in the solar system, but at interstellar scales, a miscalculated slingshot is not a small error. If your trajectory dips too deep into a star's gravity well, you might pick up more speed, but you also take a massive radiation hit, and maybe a thermal hit if your shields and radiators aren't perfect. Worst case, you skim too close and suffer heating or particle doses that sterilize your ship. The margin between efficient assist and lethal flyby can be small when you're moving at a big fraction of light speed. And stars don't just sit quietly. The heaviest ones die in some of the most violent ways the universe has, as supernovae. When a massive star runs out of fuel in its core, its outer layers collapse and then rebound in a huge explosion. In that event, it releases intense gamma rays and floods surrounding space with high-energy particles. Models suggest that if Earth sat within about 30 light-years of a typical core collapse supernova, our ozone layer could be badly damaged, and surface radiation levels would shoot up. For a planet with a thick atmosphere and a magnetic field, that's serious but maybe survivable. For a thin-skinned starship with limited shielding and no deep atmosphere, that danger zone is even harsher. The good news is that this doesn't mean the galaxy is a constant minefield of supernova kill shots. Massive stars are rare, and that they don't live very long by stellar standards, only millions of years. We can see where most of them are. We can model their remaining lifetimes, and we can plan routes that avoid the obvious high-risk zones, like dense star-forming regions packed with big, hot stars nearing the end of their lives. The bad news is in the timescales again. You're trying to predict which stars will explode and when, over tens or hundreds of thousands of years of travel. Our models for stellar evolution are good, but not down to this one blows in exactly 84,000 years. Avoid this radius from the year 85,000 to 86,000 of your journey. On top of that, stars move, clusters drift, individual stars orbit the galaxy and their positions relative to your path change over time. So your navigation system and your astronomers on board would have to keep watching, keep updating catalogues, and keep adjusting route plans across entire civilizations. Overall, if you launch one single ship, the probability that it gets taken out early by some random close pass near a dangerous star, or by sitting in the wrong place when a nearby supernova fires, is small compared to the simpler risks we already talked about. Engine failure, ecosystem collapse, radiation, and time itself. Those things are almost guaranteed to press you constantly. A supernova within 30 light years of your exact position, at just the wrong time, is comparatively rare. But if you imagine not one ship, but a whole wave of them, hundreds or thousands of galaxy escape attempts over many millennia, the statistics shift. Some small fraction of those missions will, by pure bad luck, pass a bit too close to an unstable star, or get caught inside the danger zone of a supernova. For those crews, the end won't come from slow bone loss or a bad harvest. It will come as a sudden, external blast of radiation from a star that died violently hundreds or thousands of years before the energy finally crossed paths with their hull. On galactic scales, that's the key point. The Milky Way gets a vote in whether you live or die, just not as often as your own hardware and biology. Most ships will probably fail because of problems they carried with them. A few will be wiped out in spectacular ways by the environment itself, by being in the wrong place at the wrong cosmic moment. And we still haven't talked about the objects people fear the most, the ones that dominate headlines and sci-fi plots, black holes and neutron stars. Those are the true monsters of gravity and radiation. But out in the real galaxy, are they actually likely to be the first thing that kills you? Or are they mostly just scary decorations you never get close to? To answer that, you have to look at how many of those compact objects really exist, how big their danger zones are, and how easy it is to accidentally hit one when you're trying to leave the Milky Way. Black holes and neutron stars sound like the obvious things that kill you in deep space, but do they actually matter for someone trying to leave the Milky Way? They dominate sci-fi, they dominate thumbnails, but when you look at the real numbers, they mostly fade into the background. They're terrifying up close, but up close is the key phrase. Start with the biggest one you know about, the supermassive black hole in the center of the galaxy, Sagittarius A. It sits about 26,000 light-years from you, right in the Milky Way's core, with around 4 million times the mass of the Sun squeezed into a region smaller than our solar system. We have watched stars whip around it at thousands of kilometers per second, tens of millions of miles per hour, their orbits curving sharply as they dive in and swing out. That's how we know it's there. If you try to cut straight through the galactic center, going anywhere near Sagittarius A would be a terrible idea. The gravitational field near a supermassive black hole gets intense. If you approach too close, the difference in gravity between your ship's front and back could stretch it. That's the tidal force problem. On top of gravity, the gas and dust falling into the black hole can form an accretion disk, a hot, bright ring that blasts out X-rays, gamma rays, and other radiation. If you aimed your starship into that mess, you'd risk being roasted, torn apart, or just completely scrambled. But here's the thing, you're not going that way. To leave the Milky Way, you don't dive into the core, you go out of the disk. You pick a direction away from the crowded central region, because that's safer and easier. Sagittarius A is thousands of light years off to the side from your perspective, and your trajectory never comes close. On a map, it's a dangerous boss fight sitting in a room you're not entering. What about the more common compact monsters, the stellar mass black holes and neutron stars sprinkled through the galaxy? The Milky Way probably has millions of black holes formed from collapsing massive stars, and a similar number of neutron stars, the ultra-dense cores left behind after some supernova. Those objects have intense gravity very close in. Neutron stars can have strong magnetic fields, pulsars can beam radiation, and black holes can form feeding systems that emit X-rays. But physically they are tiny. A typical stellar black hole might be a few tens of kilometers across, maybe tens of miles. A neutron star is about the size of a city, around 20 kilometers, roughly 12 miles across. Even if you count the region where their gravity really starts pulling you in hard, the target area you'd have to hit is microscopic, compared to the scales you're traveling. The galaxy is 100,000 light-years wide. These objects are specks inside that volume, so the chance that your randomly chosen route over 10,000 light-years just happens to line up with the tiny capture zone of a black hole or neutron star, without you noticing and correcting course, is effectively zero. Their gravity does extend far beyond their surfaces, but not in a way that sucks you in from huge distances. If you fly past at a sensible distance, they just behave like any other massive object. They bend your path a bit, and that's it. The real danger from compact objects isn't the hole or the star itself, it's what happens when they're actively feeding. In an X-ray binary, for example, a black hole or neutron star pulls matter off a normal companion star. That matter spirals in, forming an accretion disk that heats to extreme temperatures and throws out bright X-rays, and sometimes jets of particles at high speed. We see these systems as intense point sources in the sky. If you were unlucky enough to fly close to one of those active systems, your ship's radiation shielding would face levels far beyond anything in the solar system. You could take a massive dose of high-energy photons and particles in a short time. Your electronics would take a beating. Your structure and crew would be under stress that your design team may never have truly tested for. But again, the keyword is close. These systems are not invisible. They are some of the brightest objects in X-rays and other wavelengths. A technologically advanced civilization planning a galactic escape route would map them, catalogue them, and then simply not fly anywhere near their beams or disks. Space is big enough that you can almost always go around. So when you step back and look at all this, black holes and neutron stars end up in a strange category for your mission. They are genuinely dangerous, but they are bad at being your first killer. They take up almost no space, they are visible or predictable when they are really active, and they're easy to avoid with even halfway decent navigation and astronomy. If your ship dies by falling into a black hole, or by getting fried next to an unseen neutron star jet, something went very wrong with your planning long before you left. They are fantastic for drama, but statistically, they are not what stops you leaving the galaxy. The universe is out to get you in less cinematic ways, through slow radiation you can't quite block, ecosystems that drift out of balance, machines that wear down, and the brutal math of a 100,000-year mission. Those are the killers you can't just fly around. And if black holes and neutron stars are mostly monsters you never meet, what does the real edge of the Milky Way look like? When you finally climb out of the bright disk and into the galaxy's outskirts, what actually changes? And does anything new try to kill you out there? To answer that, you have to move from the dense, bright parts of the galaxy into its faint outer structures, the stellar halo, the hot gas around it, and the huge, dark matter halo that you can't see at all. By the time you actually climb out of the Milky Way's main disk, you've already survived almost everything that was realistically going to kill you. Out here, the galaxy looks different. The thick band of stars that once wrapped across your sky starts to narrow and thin. You're moving into the stellar halo, the outskirts, where the Milky Way stops feeling like a crowded city and starts feeling like a huge, half-empty parking lot. As you rise thousands of light years above the plane, the number of nearby stars drops. In the disk, stars are packed into a relatively thin layer. In the halo, they are spread out in a big, roughly spherical cloud that can extend tens of thousands of light years above and below the plane. Most of these halo stars are old and metal poor, meaning that they formed early in the galaxy's history and don't have many heavy elements. You also see globular clusters, dense balls of hundreds of thousands of ancient stars orbiting far from the center. In some ways, this is safer territory. Fewer stars around you means fewer chances for close passes, fewer supernova candidates, fewer dense gas clouds. The sky gets darker, the average radiation from nearby stars gets lower, and the odds of stumbling near something violent drop. But that emptiness comes with its own problem. There are fewer resources. Inside the disk, you at least have the option, in theory, of mining asteroids, tapping gas clouds, or stealing energy from nearby stars. In the halo, those options are spread much thinner. If your ship was counting on refueling or grabbing matter along the way, this is where that plan starts to fail. On top of the visible stars, you're flying through something you can't see at all, the galaxy's dark matter halo. When astronomers measure how fast stars and gas orbit in the outer regions of the Milky Way, they find that the visible mass isn't enough to hold everything together at those speeds. The solution is dark matter, some kind of substance that doesn't emit light, but does add gravity. The best models say there is a huge halo of this stuff around the galaxy, stretching maybe hundreds of thousands of light years out, with several times more mass than all the stars, gas, and dust you can actually see. For your ship, dark matter is almost a non-issue physically. Whatever it is made of, it barely interacts with normal matter, except through gravity. It doesn't slam into your hull like dust. It doesn't give off radiation you have to shield against. Flying through the dark matter halo is like flying through a gravitational field that's a bit stronger than what the stars alone would create. But you're already navigating gravity on galactic scales. It doesn't add a new killer. It just quietly shapes the orbits of everything, including yours. There is, however, another component out here that does touch you directly: hot halo gas. Observations in X-rays show that the Milky Way is wrapped in a very thin corona of ionized gas with temperatures of around 1,000,000 degrees Celsius, or Kelvin. That sounds insane, but temperature here just means the average kinetic energy per particle. The density is extremely low, something like 1/10,000th of an atom per cubic centimetre, much less than even the interstellar medium in the disk. At everyday speeds, you could move through that gas and barely notice it. At a fraction of light speed, those individual particles that do hit your ship deposit high energy in tiny spots. They contribute to erosion of your forward shields and to the radiation dose on the crew. But this isn't a brand new kind of threat. It's just more of the same cosmic ray-style grinding you've already been living with. High energy particles, slow material loss, more impacts to add to your long-term damage budget. So the halo itself doesn't spring a surprise attack on you. There's no sharp line you cross where conditions suddenly flip. There is no hard edge where dark matter slams into you, or where halo gas becomes a solid wall. Instead, you experience a slow transition. Star density falls. The Milky Way's bright band thins in your sky until it looks more like a flattened, distant object behind you. The gravitational pull from the galaxy is still very real, but the local environment gets emptier and harsher at the same time. For the crew, subjectively, nothing magical happens at some exact border. One day looks a lot like the next. Radiation levels might tick up a bit. The night sky might look a little sparser. The real change is psychological. If you've made it this far, you have already outlived the original launch civilization. You've beaten rocket risk, solar storms, heliosphere exit, cosmic rays, dust impacts, skeletal loss, ecosystem drift, and internal social collapse. At least so far. You are now so far above the galactic plane that the sun, if anyone still remembers which one it is just another dim point buried inside a distant glowing disk. The important truth here is that the Milky Way's border patrol is weak. The galaxy doesn't throw some special new weapon at you in the halo. Most of its serious threats are back in the disk and inner regions. Dense star fields, supernovae zones, strong radiation environments. Out here, the biggest problem is not that something new appears. It's that support and resources disappear. You are truly on your own. No nearby stars to harvest easily, no friendly planets to land on, no rich belts of asteroids everywhere you look. If you're still alive by the time you're deep in the halo, you've already beaten odds that were stacked almost completely against you. You've pushed a fragile biochemical species and a complex machine ecosystem through a test they were never designed for. The galaxy hasn't stopped you at the edge. The real question now shifts again, away from can you get out of the Milky Way, and toward what happens once you're beyond it. Because past the halo, the sky gets even darker. The galaxies thin out into a vast, low-density network. Between those islands of light is the largest desert you can imagine. Space so empty that a cubic meter might be almost perfectly clear of atoms. So if you somehow reach that region, beyond the comfortable reach of any galaxy, what does that final environment look like? And what does it do to a ship that's already been fighting for survival for tens of thousands of years? Once you're really past the Milky Way's halo, you are not in more space like before, you are in something qualitatively different. Inside a galaxy, even in the outskirts, there's always a nearby star, some gas, some dust, some structure. Between galaxies, all of that drops to almost nothing. From a survival point of view, this is not just empty, it is hostile by absence. There is nothing to work with. In the intergalactic medium, the average density of matter falls to about 1/1,000,000th of a particle per cubic centimetre, sometimes even less. That's roughly one lonely atom in a volume the size of a house. Not a cubic meter, a house-sized volume. There is still structure on the largest scales, thin filaments of slightly denser gas connecting clusters of galaxies, but huge regions between those filaments, called voids, can stretch tens of millions of light years with almost no matter at all. On Earth, if you're stranded in a desert, at least there's air, some trace water, rocks, maybe plants. In intergalactic space, from a resource point of view, you are worse off than standing in the middle of the Sahara with no water and no atmosphere. For a starship that needs a certain density of gas for fuel or solid material for repairs, this environment might as well be a perfect vacuum. Inside a galaxy, your theoretical options are at least there. You could park near a star and use its light to power solar arrays. You could mine asteroids for metals. You could scoop gas from molecular clouds. You could, in principle, refuel. Outside, in deep intergalactic space, most of those doorways slam shut. The only light around you is faint glow from distant galaxies and the low-energy radiation of the cosmic microwave background at about 2.7 Kelvin, just a few degrees above absolute zero. At those brightness levels, solar panels are useless. There is no star close enough to deliver meaningful power. Fusion scoops don't help you either, because there is almost no hydrogen per unit volume to collect. You can try for incredibly large collectors and insanely long collection times, but practically, that's not a fuel source. For propulsion and power, you are stuck with what you carried out of the galaxy with you. That shifts the design constraints of your mission in a brutal way. You can't count on finding fuel or materials once you're between galaxies. If your reactor fuel runs low, that's it. If your reaction mass for propulsion is gone, you can't turn, slow down, or correct course. If a key material runs out, some trace isotope crucial for your life support or your electronics, you don't get to go mining. You just don't have it anymore. You either launch with every kilogram you will ever need, or you die when something finally runs out. Astronomers have actually mapped this structure on large scales. Surveys like the Sloan Digital Sky Survey have charted the positions of hundreds of thousands of galaxies. When you plot them, they form a kind of foam or web. There are dense clusters where many galaxies group together, thin filaments connecting them, sheet-like structures, and then big hollow regions, voids, where there are far fewer galaxies. Those voids are not perfectly empty, but for a ship that wants nearby stars or simple refueling stops, they might as well be. Now look at distances. The Milky Way's nearest major neighbour is the Andromeda Galaxy, about 2.5 million light-years away. That is incredibly close in cosmic terms. They are part of the same small group. But for a crewed mission with any remotely normal constraints, 2.5 million light-years is completely out of reach. Even at 0.1 C, which was already insane to engineer, that crossing would cost you roughly 25 million years of ship time. That's about 300 times longer than anatomically modern humans have existed on Earth. And that is one of the closest big galaxy pairs in the entire universe. Most galaxy separations are larger. So, from a practical point of view, once you are truly between galaxies, you're not on your way somewhere in a human sense. You're just out there, in a region that no biological crew can reasonably cross. This leads to a very cold conclusion. If you fail out here, nobody comes. There are no neighbouring space agencies, no friendly civilizations just over the horizon with a rescue craft. Even if another advanced species existed in a nearby galaxy, the combination of distance and low density makes rescue effectively impossible. Signals take millions of years to cross. Vehicles would need impossible energy budgets. If your life support finally fails after 100,000 years of struggle, if a crack appears in your reactor that you can't fix, if your descendants decide they are done maintaining the systems their ancestors built, your ship doesn't crash into anything. It doesn't burn up. It just becomes a dead object, an aluminum and composite coffin drifting through a region that will stay almost exactly the same for billions of years. No one notices. No one finds you, unless some far future archaeologist with absurd technology deliberately hunts you down. This is the purest form of isolation the universe offers. In low Earth orbit, you can see your home planet below. On Mars, at least the sun is still bright and Earth is a point in the sky. In the galactic halo, the Milky Way is still a huge structure you can look back on. In intergalactic space, your home galaxy shrinks to a dim patch of light, one smudge among many. There is no up or down, no obvious direction that looks safer. It's just you, your ship, and a background of distant galaxies that might as well be painted on a wall. If your mission fails in the disk, the story ends near where it started. If it fails in the halo, at least it fails near one of the great structures of the universe. If it fails out here, between galaxies, it's like the universe barely even registers that you tried. From a physical point of view, nothing changes. From your point of view, though, this is the absolute maximum cost of a mistake. You gambled everything. You got past almost every barrier, and you died in a place where nobody will ever even know you existed. And yet, even this ultimate desert is not the final limit. There's one more layer of difficulty above all of this. One that doesn't care about your engineering or your bravery. It's not about where matter is. It's about how space itself behaves over cosmic time. Because on the largest scales, the universe is not static. The fabric of space is stretching, and that slow expansion quietly decides which galaxies are even reachable in principle, no matter how advanced you become. So after fighting rockets, radiation, dust, biology, ecosystems, stars, and sheer emptiness, there's one last question. Does the universe itself, through cosmic expansion, eventually make leaving the galaxy not just hard, but physically impossible? Even if you beat every local problem and actually get ships between galaxies, there's a bigger issue running in the background. The universe itself is changing under your feet. On very large scales, galaxies are not just sitting still in a fixed grid. They are all moving away from each other because space itself is expanding. And that expansion slowly decides which destinations are even reachable in principle. We describe this big-scale motion with something called the Hubble flow. When astronomers measure how fast distant galaxies are receding from us, they see a simple pattern. The farther away a galaxy is, the faster it appears to move away. The rate is set by the Hubble constant, roughly 70 kilometers per second for every megaparsec of distance. A megaparsec is about 3.26 million light-years. So if a galaxy sits 1 megaparsec away, it recedes at about 70 kilometers per second. At 10 megaparsecs, 700 kilometers per second. At hundreds or thousands of megaparsecs, the recession speeds become a big fraction of the speed of light. This is not because galaxies are all flying through pre-existing space like bullets. On those scales, you should think of space itself stretching, so the distance between galaxy clusters grows over time. Locally, gravity binds things together, like stars bound into a galaxy, or galaxies bound into a small group. But beyond a certain scale, the overall expansion wins. That's why very distant galaxies all show a redshift, their light stretched to longer wavelengths as space expands on its way to us. It gets worse. Observations of very distant supernovae show that this expansion is not just continuing, it's accelerating. Something we call dark energy is pushing on the universe in a way that speeds up the stretching over time. We don't know what dark energy really is, but we see its effect in the data. As the universe ages, the space between unbound galaxy groups grows faster and faster. That acceleration means there is a kind of cosmic horizon. Beyond a certain distance, galaxies are receding so quickly that no signal we send, not even light, can ever catch up. As time goes on, more and more of the universe crosses that horizon from our point of view. Those regions don't disappear, but they become forever unreachable. They slide out of our causal contact. Right now you live in a special window. The Milky Way, Andromeda, and a few dozen small galaxies make up the local group, a little island of matter where gravity is strong enough to override expansion. On even larger scales, we're part of a bigger structure, the local sheet, and then the Virgo supercluster, and then larger networks. But those are not all gravitationally bound in the same way. Over many billions of years, dark energy wins. The local group holds together. Everything else drifts away. If you fast forward tens of billions of years, the story gets very narrow. The Milky Way and Andromeda are on a collision course right now. In about 4 to 5 billion years, they will merge into a single massive system, sometimes nicknamed Milkdromeda. Any smaller galaxies in the local group will either merge in or orbit as satellites. On the sky of that far future, distant galaxies outside the local group will grow fainter, then redder, and eventually slip past that cosmic horizon. Their light will no longer reach you at all. For a civilization born in that far future, the visible universe will look small and empty. Only their own merged supergalaxy will be bright. Everything else will be gone from view, both visually and causally. For them, the question, can we leave the galaxy, has a different answer. It's not just hard because of engineering, biology, or distance. It's hard because the universe has literally locked the exits. No amount of propulsion, even at light speed, can take them to galaxies that have already receded beyond the horizon. Their only playground is that single, local structure. This is a crucial shift. Cosmic expansion does not tear your ship apart. It doesn't rip atoms or planets or galaxies to pieces at human scales. Inside a galaxy, gravity dominates, and expansion is effectively zero. You will not feel being stretched on your starship. What expansion does is more subtle and more final. It sets absolute limits on where you can go if you wait too long. It shrinks the list of reachable destinations over cosmic time until it contains only your local group, then only your merged home galaxy, and eventually only your immediate neighborhood of stars. So from your point of view today, cosmic expansion is not the thing that kills you first when you try to leave the Milky Way. You will die from something else, long before dark energy matters to your personal mission. But expansion defines the endgame. It means that leave the galaxy is not a timeless question with the same answer forever. In the deep future, that move becomes not just extremely unlikely, but physically impossible beyond a certain scale. Put that together with everything else you've heard. The rocket equation fights your engines, radiation fights your cells, dust fights your hull, time fights your social systems and your technology, ecology fights your food and air, and slowly, cosmic expansion shrinks the playground you're allowed to try all this in. The deeper truth hiding behind "Can I leave the Milky Way?" is that on almost every level, the universe is biased toward no, but that still leaves one piece. After all of these layers, you want a straight, practical answer. If you, right now, with any technology that is even vaguely connected to known physics, tried to lead a mission to leave the Milky Way, what actually kills you first? Is it your rocket? Is it radiation? Is it dust? Is it age, or is it the slow collapse of your own tiny world? To wrap this up, we need to take everything we've stacked so far, sort it by what hits you soonest and hardest, and say clearly where the real killer is hiding. So after all this, if you actually try it, what kills you first? Not in theory, not in some far future fantasy, but starting from the tech and biology you really have, plus maybe one or two big breakthroughs. With anything close to near future technology, the answer is simple. You never give the galaxy a fair chance to kill you. Chemical rockets, maybe nuclear thermal stages, maybe a very basic fusion concept. They can push probes to interesting speeds, but they do not give you the delta varbs you need to get anywhere near the edge of the Milky Way. You're struggling just to reach nearby stars in tens of thousands of years, never mind leaving the disk. In that regime, the trip that actually flies is not a leave the galaxy mission. It's a deep space expedition on the scale of a few years to a few decades at most. On those timescales, your likely killers are very familiar. Your rocket stack is still a bomb compared to everything else on board. So engine failure or tank failure can end you minutes after launch. Your life support is still a chain of pumps, filters, scrubbers, and software that can break. And once you're outside Earth's magnetosphere, your radiation exposure climbs into ranges where, over a few years, your cancer risk spikes. So in a realistic next century attempt, there are three main ways you die. The vehicle blows up, the systems that keep your air and water and temperature in range fail, or the radiation dose you take over a multi-year mission gives you life-shortening disease. In all those cases, the edge of the Milky Way is just a background concept. It might as well be the Andromeda Galaxy, nice to look at, but completely irrelevant to your actual cause of death. You never even get close enough for the shape of the galaxy to matter. Now give yourself more freedom. Say you invent a miracle drive that can push a big ship to between 0.1 and 0.9 times the speed of light. Call it 30,000 to 270,000 kilometers per second. About 18,600 to 167,000 miles per second. You solve the rocket equation in some advanced way. You handle the insane energy budget. You harden your hull against dust grains and cosmic rays. You've done everything a superstar engineering civilization could reasonably do. Even then, one thing hasn't changed: the clock. At 0.1 C, getting 10,000 light-years out of the disk still takes about 100,000 years. At 0.9 C, relativity helps, but you still face tens of thousands of years of ship time for really deep excursions. Human biology has not suddenly stretched to match that. A human lifetime is still around 70 to 80 years if you're lucky. Maybe future medicine pushes that to 120 or 150. You're still off by orders of magnitude. So if you, personally, got on that ship with that miracle engine, and you did not have any way to pause or radically slow your aging, the first thing that kills you is still basic. You get old, and you die long before the mission reaches anything like outside the galaxy. Maybe your grandchildren see a small shift in the star field. Maybe their grandchildren see the Milky Way's band get thinner. Nobody on board at launch survives to see real galactic escape. To beat that, you need something as radical as the drive itself. Real suspended animation that works for centuries, or bodies replaced or backed up by digital minds, or biological immortality with perfect repair of cellular damage. Without one of those, the physics of the journey says the main killer for any individual on a fast ship is just age. So you shift the plan again. You say, fine. This isn't about one person's life. It's a generational arc. Thousands of people live in a huge rotating cylinder that simulates 1G. They have thick shielding, fusion reactors, closed ecosystems, and advanced automation. Children are born on the ship, grow up there, learn the systems, and keep it going. On paper, that can last as long as the hardware does. In that setup, the first killer is almost never some single external event. Radiation and microgravity damage become background problems that you can mostly manage with shielding and artificial gravity. At least for a while. Dust impacts are serious, but you have massive forward shields and active defences. Propulsion is dangerous, but you're probably only doing big burns at the start and end, not all the way. The main threat shifts inside. Your own ecosystem and your own social and technical stability. Your food and air depend on bioreactors, crops, algae, microbes, water loops, and nutrient cycles staying in balance. Your power depends on reactors that need maintenance and possibly fresh fuel. Your culture depends on each generation learning enough to operate and repair all of this without slowly drifting into ignorance or neglect. Over thousands of years, the odds that nothing important ever breaks in an unfixable way are very low. Maybe a key algae species in your air system mutates and starts producing a toxin. Maybe some slow chemical process locks away a vital nutrient, like phosphorus or iodine, and nobody notices until health problems spread. Maybe a collapse or civil conflict destroys infrastructure faster than people can rebuild it. You don't get a neat cinematic disaster. You get air that is a little worse each decade, crops that yield a bit less, more frequent equipment failures, more patched-together fixes. So for a generational ship that somehow avoids early accidents, the likeliest first true mission-ending event is ecological or systemic. 1 year in the far future. Maybe year 7,342 or 23,000 or 80,000 of a planned 100,000-year trip. Something in your closed life. Support web crosses a threshold. Oxygen production falls and can't be brought back up. Food production crashes. A critical reactor fails and you don't have the resources or knowledge left to rebuild it. The immediate cause of death looks very basic. No breathable air, no safe water, no calories. But the root cause is that a complex closed system forced to run for geological timescales finally hits a failure it can't recover from. That's the pattern when you stack all the scenarios. With tech like ours, you die from rocket failures, life support breakdowns, or manageable duration radiation, long before the galaxy matters. With sci-fi drives but normal human bodies, you die of aging long before you see the edge. With sci-fi drives and a properly designed arc, you most likely die when your biosphere or your long-term maintenance and social systems finally slip past the point of no return. In all of these, black holes, dark matter, the galactic edge, and cosmic expansion are background. They shape the problem, but they don't swing the first punch. So the punchline is blunt. If you try to leave the Milky Way with anything like biological humans in a rocket-based civilization, The first and most dangerous obstacles are not out in the galaxy. They're the limits of your engines, the fragility of your bodies, and the instability of your own artificial world over huge spans of time. The Milky Way is big and mostly indifferent. It doesn't need a sharp boundary or a hidden monster to stop you. It just lets your own weaknesses and the sheer length of the journey do the job. That's the answer to the original question. What kills you first if you really try to leave the Milky Way? In every realistic scenario, it's not the galaxy that kills you, it's you. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.